Okay, a couple more examples of how natural logs or just logs in general can be really helpful for us. Is there's actually something called logarithmic differentiation. This isn't necessarily a really common topic, but it is something that could be helpful if you're looking for kind of a way to get out of a jam sometimes, or a way to actually make some of your derivatives maybe just a little bit easier. Let's say, for example, you have something like, let's just go to a pretty straightforward example of a product rule here. So you have something like y equals x squared times the sine of x. Um, Notice there's no logarithms in here right now, but sometimes creating logarithms or adding logarithms into the problem because of different log properties actually could help yourself out and make this a little bit easier. For example, if you didn't want to have a product rule here, or there's times where this is a fairly straightforward example, by the way. There's times where we could have a function that's a lot more complicated, and logs can really be helpful. What you could do is you could say, let me take the natural log of both sides first, because when you take the natural log of the right side, you may remember some of your log rules from past classes. When you have the natural log or any kind of log of two things multiplied together, it's actually perfectly fine to write that as the natural log of x squared plus the natural log of the sine of x, and split that up into two separate logs. Okay. Um, I don't know. I mean, you can decide whether you think that would be helpful, but there's times where it could be helpful to take products and quotients and kind of split them up into sums and differences using log rules like this. Okay, and exponents sometimes. You can move exponents down in front. So, for example, the natural log of x squared, another way to write that is to write it as 2 times the natural log of x. So there's ways you can kind of simplify things by using log rules to make your derivatives, the actual derivatives you're calculating, just a little bit easier. Okay, and I tell you what, I guess I will go ahead and leave that as a 2 out in front, 2 times the natural log of x. So we could pull that exponent down in front because of log rules. Okay, now go ahead and take the derivative of of both sides of the equation. So d over dx of the natural log of y over here is 1 over y times the derivative of the inside. There's a chain rule because it's a y, so times y prime. Take the derivative of 2 natural log of x. Well, that's 2 times 1 over x. And then take the derivative of the natural log of the sine of x. That is 1 over the sine of x times, there's a chain rule in there, so times the derivative of the sine, which is a cosine of x. And this whole thing kind of simplifies a little bit to look like I guess I'll go up here. I don't want to go to a new board right now, but we'll go up here and we can simplify this a little bit. This is y prime over y equals 2 over x plus, let's see, you have a cosine on top and a sine on the bottom, so plus a cotangent of x. Now get y all by itself. That's not too bad. Or I'm sorry, get y prime all by itself, and you can move the y to the other side. You can even substitute back in for y the fact that you have an x squared times a sine of x. So y prime here actually ends up being 2 times x squared times the sine of x all over x plus x squared times the sine of x times the cotangent of x. And you can actually simplify this further because the cotangent has a cosine on top and a sine on the bottom, so the sines will cancel. You can cancel an x over here as well. Again, you could have done this without using logarithms, but just a way to be able to see how those could be useful for us to be able to take derivatives of something that's a little bit more complicated with a lot of products and quotients in there. So let's see, we can cancel an x on top and on bottom. We get 2x times sine of x, and then let's see, you can cancel this sine of x with the sine that's on the bottom. It becomes an x squared times a cosine of x. Okay, so that would be our final answer right there, which that would be the final answer if we did a product rule from the beginning, but again, just a different way to see it like that. Okay, one last thing we want to be careful about is where is your variable? Okay, so it can be a little bit hard to identify sometimes, but it's a really good question for you to ask, because do we have something like 2 to the x, or do we have something like x squared? We kind of had an example of that in a past video that kind of distinguishes the difference there a little bit. But if you have if you have your variable up in your exponent, this is an exponential example. If you have your variable down in your base, This is a polynomial example. There's actually a third situation that we really haven't seen almost ever because there's not much we can do with it, and that is what happens if you have a variable both in the base and up in the exponent. Okay, that is not easy to be able to deal with because if you try to move the exponent down from up in the exponent, or the variable down from up in the exponent, now you have a log of an x in there, and you kind of have x's on different levels, which is a little bit tricky to deal with. But in this, we can still go ahead and find y prime, but before we try to take a derivative, what would be really helpful here, I think, is to take the natural log of both sides. The natural log of y equals, so this is just kind of a rewrite of that equation. I probably shouldn't put equals there. This is a rewrite. So the natural log of y is equal to the natural log of x to the x. And the reason that might be useful is because when you have, again, your log rules from past classes, when you have a natural log of something with a power, that power can drop down in front. So this is x times the natural log of x is equal to the natural log of y on the left side. And so now, could you go find y prime, now take the derivative of both sides of the equation. So take d over dx of natural log of y. That's 1 over y times y prime. And then take the derivative of the right side. Well, there's a product rule in there, so be careful with that. The derivative of that product rule looks like the derivative of the first, which is 1, times the second, plus the first, times the derivative of the second. The derivative of the second is 1 over x. And so really this x and this x on the bottom are going to cancel there, and that's okay. We end up getting something like y prime over y is equal to the natural log of x plus 1. And then again, go ahead and solve for y prime. Okay, I'm going to put that over here to the left. So get y prime by itself. This looks like 1 plus the natural log of x all times y if you move that y to the other side. But remember what y is at the beginning. Y is x to the x, which is weird, but at least we can find y prime there. And this equation here, y prime equals, only has x's in it, no y's. So a weird case, a weird situation to take a look at, but at least we can work with that when we're talking about having an x in both the base and in the exponent by using logarithms. Honestly, there's really no other way we could deal with that type of equation if we didn't use logarithms, because we don't know how to deal with the x that's in both the base and up in the exponent at the same time. So just be really, really careful about where your variable is, okay? Because that'll dictate whether you need to use a power rule, whether you are using exponentials, whether you need to use logarithms. What does that look like? This is why we want to kind of have all these rules laid out and keep them all straight, and then know really carefully which rule you want to be able to use when. Okay, so this is derivatives of logarithms. I hope you've enjoyed. Good luck practicing.